So reaction with HCN. Reaction with HCN. Number 1 reaction, nucleophilic addition reaction. Addition of hydrogen cyanide. Number 1. See the reaction. Hydrogen cyanide being a weak acid, we take an alkali medium to facilitate the nucleophile readily available. HCN is a weak acid, everybody know. So if you want the nucleophile sufficiently available, let us take alkali medium where it neutralizes, giving sufficient nucleophile. Okay. Now that nucleophile attack on C plus center, there is a polarization O minus, C plus, the Cn minus will be attacked and you get a tetrahedral intermediate. You get a tetrahedral intermediate. Here carbon is sp2 planar system and here carbon turn sp3 tetrahedral. So this is the rate determining step of the reaction where the nucleophile is added and hence it is called a nucleophilic addition reaction. And now there is proton capture H plus, O minus captures H plus and you get the final product Cn and OH, cyanohydrin. It is called a cyanohydrin, right? So the reaction happens with the alkali medium so that we get a cyanide ion sufficiently available. And is also commented cyanohydrins are useful synthetic intermediates. How cyanohydrins are useful synthetic intermediates? How cyanohydrin turn useful synthetic intermediate? You look at the cyanohydrin. For example, if you take RCHO when treated with HCN and finally you get a cyanohydrin, there is OH, CN, H and R. How this turn a useful synthetic intermediate? Very simple. This OH group can be substituted with the various other groups. You can bring in various other groups in the place of OH, number 1. Number 2, this upon hydrolysis, you can get carboxylic acid. This upon reduction, you get amine. Hope you understand. So CN can be made to carboxylic acid or amines, right? Number 1. OH group can be replaced with the various groups introduced at that position. So there are multiple choices of converting that compound into different requisite forms. And that's how it acts as a useful synthetic intermediate. Okay. So that's about first reaction with the hydrogen cyanide. Next one, addition of sodium hydrogen sulfite. Addition of sodium hydrogen sulfite. You look at the reaction, addition of sodium hydrogen sulfite, Na plus and HSO3 minus. This is HSO3 minus. This is Na plus and O minus. This is SO3, like this, right? So there is a polarization O minus and C plus. So the C plus will be attacked by this group. That is OSO2H. OSO2H. In fact, the molecule is here it is NaHSO3, no? NaHSO3. So how is going to be that? Na plus O minus and here it is OH, right? OH. So it is O. This is the unit which is attacking on the C plus center. OSO2H. OSO2H. This group will be acting as the nucleophile and Na plus will be coming with the oxygen. So you get O minus turn ONA and C plus connected with this nucleophile. What is a nucleophile? OSO2H. OSO2H. Rather it is OSOOH, like that. Right? That is the sodium hydrogen sulfide addition product. Same way, nucleophilic addition reaction, and thereby you get a tetrahedral addition compound. Tetrahedral addition compound where there is a proton transfer. This H plus will be transferred to this place and Na comes here. Because this is an acid unit, this is a distinctly acid one when compared to alcohol group. Alcohol group has to be like that and acid should be in the neutralized form. So there is a proton transfer from here to here. ONA turn OH and SO3H, OSO2H turn OSO3, SO3H turn SO3Na or OSO2Na. Right? Sodium hydrogen addition product. This is very useful for the identification, separation of simple aldehydes and ketones. If you consider aldehydes, the equilibrium will be more towards the right hand side. There is a greater reactivity. In case of ketones, reactivity is rather less. Mainly, you know the reason, and that is what we were discussing few minutes back regarding the electronic reasons, regarding the steric reasons, right? So reaction number 1, addition with HCN, you get a cyanohydrin. Reaction number 2, reaction with the sodium hydrogen sulfide. First, you are getting such an addition product, which upon proton transfer, you get this product, which is obtained as a crystalline product. It's a useful technique, simple useful technique for the identification, separation of simple aldehydes and ketones, particularly aldehydes. Okay. And next reaction, it is already learned in the previous chapters. Addition with the Grignard reagent. Addition with the Grignard reagent. Hope you remember how Grignard reagent interact with the carbonyl compounds. Carbonyl compounds interacting with the Grignard reagent. Detailed learned in the previous chapter, where you can see CO polarizes as O minus and C plus. It is breaking here as Mg plus and R minus. R minus getting connected to this and O minus interacting here. And you get the addition product. You get OMgX and R comes here. This is the addition product obtained, which upon hydrolysis O will become OH and the final product will be like this. OMgX becomes OH and there is R, like this. You get a alcohol. Final product is alcohol. And now, if you are dealing with the formaldehyde, HCHO, the final result will be CH2OH. You get a primary alcohol. Already learned, I am just reminding you. So, if you take formaldehyde, the final product will be primary alcohol. And if you are taking any higher aldehyde, the final result will be CHOH, a secondary alcohol. Any higher aldehyde taken, the final result will be secondary alcohol. And if you are taking a ketone, it is COH, you get a tertiary alcohol. A ketone, say for example CS3, COCS3, you get a tertiary alcohol. This much in the content point we have learnt, right? And further there are more reactions. How Grignard reagent reacting with the HCN, how it reacting with the RCN, how it is reacting with the ester of formic acid, how it is reacting with the epoxides, how it is reacting with the substituted epoxides, how they are reacting with the higher esters. Right? So all need to be discussed, particularly the 3 reactions, that is dealt in the NCERT. Reaction with the formaldehyde, giving primary alcohol, reaction with any other aldehyde, giving secondary alcohol, and reaction with the ketone. First you get a addition product and final hydrolysis product is tertiary alcohol. Learned in the previous chapter, Just I was reminding you. So reaction number 1 with HCN, reaction number 2 with the sodium hydrogen sulfide, and reaction number 3 Grignard reagent. Most important one, reaction with the alcohols. Reaction with the alcohols, that is addition reaction with the alcohols. Aldehydes get added with the monohydric alcohols in presence of dry HCl gas. In presence of dry HCl gas, aldehydes react with the monohydric alcohols. Suppose I am taking an aldehyde. This is an aldehyde which interact with the monohydric alcohols, ROH. Monohydric alcohols, R-OH, in presence of dry HCl gas. In presence of dry HCl gas, the reaction will be shifted to forward direction, while with the dilute H plus, with the dilute HCl, the reaction will be driven backward. And see what is the reaction happening? Very simple. It's very similar way, O minus and C plus, and it is breaking over here, H plus, O minus. This RO minus will act as the nucleophile, and the result will be there is R, there is H, C, O, R dash, and OH. This O minus will attract H plus, and this is called hemiacetal. Hemiacetal. So aldehydes react with the monohydric alcohol. 1 mole if it react, you get hemiacetal. Hemiacetal. So definitely means it can react once again. It can react once again. It may react with 1 more mole of alcohol, where you can see OH and H out, and you get acetal formation. This turn OR dash, and this also turn OR dash, and this is called acetal. Acetal, that is the final product. So aldehydes react with the monohydric alcohol 2 times. You get the first hemiacetal and followed by acetal. Remember, it is triggered by HCl gas. HCl gas is sufficient enough to protonate a CO group. Particularly this O is getting protonated by HCl gas, and that increases the electrophilicity of C plus, and that trigger the reaction. While if you take a dilute HCl, it will actually hydrolyze this system. Dilute HCl will hydrolyze this system, and the reaction will be reverted. That means hemiacetal or acetal can be reverted to aldehyde by hydrolysis, dilute acid medium. Right? So remember, aldehydes react with the monohydric alcohol. Then ketones react with the, all of you may be remembering, dihydric alcohol. Ketones react with the dihydric alcohols. Look at the way ketones are reacting. This is a ketone. It is reacting with the dihydric alcohol. Say for example, ethylene glycol. Say for example, ethylene glycol. It is interacting with the dihydric alcohol. And what is the final product? The final product obtained is CH3, C, CH3. You get it like this. You get cyclic ketol. This is called a cyclic ketol. There is cyclic ketol formation. Ketones interact with the dihydric alcohol, giving cyclic ketol formation. Hope you understand. Based on which several times questions came. So aldehydes interact with the monohydric alcohol. First you get hemiacetal and then you get acetal. While ketones interact with the dihydric alcohol, where you get cyclic ketol. Okay. So that's about the reaction of alcohol with the alcohol with the carbonyl compounds. So reaction number 1, HCN addition. Reaction number 2, addition with the sodium hydrogen sulfide. Reaction number 3, addition of Grignard reagent, already dealt in the previous chapter, and here addition of alcohols. Remember, the reaction is driven forward direction by dry HCl gas, and the reaction revert in dilute HCl gas, HCl solution, right? Dry HCl gas is sufficient enough to protonate the CO oxo group O, and thereby facilitating greater C plus charge, which facilitate the nucleophilic addition over the carbonyl carbon. Okay. Next is a very importance of series of reaction. Reaction with ammonia and derivatives. Reaction with ammonia and derivatives. Addition reaction with ammonia and derivatives. Addition of ammonia and its derivatives to carbonyl system, right? So it is basically a nucleophilic addition reaction followed by elimination of simple molecule like water. It's basically some sort of condensation type reaction, right? Let's see the reaction. Carbonyl compounds undergoing addition followed by elimination with the ammonia and derivatives. So we can have the general reaction like this. This is carbonyl compound, maybe aldehyde or ketone. It is interacting with the ammonia and its derivatives. There is a sequence of reaction. So I am writing ammonia and derivatives in the general format NH2Z. NH2Z. So we can keep on changing Z for the various types of different examples involved in that sequence. Okay. Say for example, if we are dealing with the reaction of ammonia, for example, first one, reaction with ammonia, how is going to be H, N, H, and in the place of Z, there will be H. So in the place of Z, if it is H, it is ammonia. Suppose we are dealing with a second reaction with amine, RNH2. It is nitrogen, hydrogen, hydrogen, R. So it is the Z part. This is the Z part. So that Z part alone keep on changing. Accordingly, we have some 6 or 7 different reactions related to ammonia and its derivatives. So to explain the ammonia and derivatives, we are writing simply Z. This undergo condensation, addition reaction first. It undergo nucleophilic addition reaction. You see what is happening? O minus and C plus is breaking over here. NHZ minus and H plus, and there will be addition reaction. It is COH and NHZ like this. So this is the addition product obtained, right? Now this addition product can eliminate simple molecule like say water. In this case, water molecule is eliminated and it undergo condensation. How water molecule is eliminated? This OH group and this hydrogen out as water. So what is the result? C double bond NZ. This is the final product. That is what the reaction. All of you know, I am just reminding you. Or simply you can understand the entire reaction. You can understand like this. C double bond O plus H2NZ. It is H2O out. Overall reaction H2O out, and the result is C double bond NZ, the final product. In fact, actually the reaction is happening like this. Ammonia or derivative, first nucleophilic addition reaction followed by elimination of water molecule, you get the final result, right? And the Z keep on changing. Z keep on changing. You see, Z keep on changing. When Z is H, it is reaction with ammonia. If it is R, it is reaction with amine. Like that, 1, 2, 3, 4, 5, 6, 7 reactions are there. Ammonia and its derivatives. Let's have a look at one by one. Okay. So first reaction with the ammonia. Reaction with the ammonia, first one. So it is going to be C double bond O. So now I am writing the entire overall reaction. I am writing it is H2NH. In place of Z, it is H. Then it is ammonia. And the result is H2O out. And it is C double bond NH. It is called imine. The product is called imine, aldehyde, ketimine, imine. That is the product. So if you take ammonia, you get imine. There are various addition products. If you take ammonia with the formaldehyde, different products are obtained. You get urotropin, various related products, commercially important products are there. But limited to the syllabus content, we are discussing the most commonly encountered reactions pertaining to ammonia or its derivatives. Number 1, reaction of aldehydes or ketone with ammonia, you get imine, number 1. Number 2, reaction with amine. So reaction number 1, reaction with ammonia, where in the place of Z, it is hydrogen. The product obtained is imine. Number 2, reaction with amine, carbonyl compounds interacting with amine. What is in the place of Z? It is an alkyl group or any group, alkyl group. Now there is water molecule out, and look at the result. It is C double bond NR. That is called substituted imine. Called Schiff's base. It is called Schiff's base. Substituted imine. So if you take ammonia, the product is imine. If you take amine, the product is substituted imine. Okay. Now the third one, in the place of H, it is going to be, this is amine. So ammonia, you get amine. Amine, you get the substituted amine, that is Schiff's base. If you take the third one, hydroxylamine. This is called hydroxylamine. You see, water molecule out, and the result is C double bond NOH. It is called oxime. Aldoxime, ketoxime, like that, oxime. So if you take ammonia, the product is imine. If you take amine, the product is substituted amine Schiff's base. And if you take hydroxylamine, very important class of product, it is called oxime, aldoxime, ketoxime. So 3 over. Now fourth one. Carbonyl compound interacting with hydrazine. What is in the place of Z? In the place of Z, hydrogen coming, ammonia. In the place of Z, R coming, amine. In place of Z, OH coming, hydroxylamine. Now it is NH2. What is NH2? Z, NH2. So it is NH2. It is hydrazine. You have hydrazine. And what will be the result? This is out again, and you get C double bond NNH2. If you take hydrazine, the product is hydrazone. This is called a hydrazone. So ammonia, you get imine. Amine, you get substituted amine. Hydroxylamine, you get oxime. Hydrazine, you get hydrazone. Okay. Next, phenylhydrazine, fifth one. Phenylhydrazine, carbonyl compound, aldehyde or ketone, interact with phenylhydrazine. This is phenylhydrazine. There is a benzene ring. NH2, NH2, hydrazine, phenylhydrazine, phenylhydrazine. It's very simple that all reactions are mere repetition. All reactions are mere repetition. Only difference is in the Z part. And accordingly, what is the name of the reagent, what is the name of the class of product, and how the class of product is coming, like that. Reaction is identical. So what is the product obtained here? It is C double bond N NH benzene ring. This is phenylhydrazine. And what is the product obtained? Phenylhydrazone. Phenylhydrazine gives phenylhydrazone. Ammonia gives imine. Amine gives substituted imine. Hydroxylamine gives oxime. Hydrazine gives hydrazone. Phenylhydrazine gives phenylhydrazone. And in fact, you know, the next one is very, very important. 2,4-dinitrophenylhydrazine, 2,4-DNP. 2,4-DNP. Carbonyl compound interacting with the 2,4-DNP. This is 2,4-DNP. In the benzene ring, you have two nitro group like this. 2,4-dinitrophenylhydrazine. 2,4-dinitrophenylhydrazine. It is called 2,4-DNP, famous known as Borchers reagent. Borchers reagent. Sometimes also called Brady's reagent. Borchers reagent or Brady's reagent. And no difference in the reaction characteristics. This is the reaction as usual, and the product obtained is C double bond N NH. This is 2,4-DNP, 2,4-dinitrophenylhydrazine, and this is 2,4-dinitrophenylhydrazone. Hydrazone. That's all. 2,4-dinitrophenylhydrazone. In fact, all of these reactions, it's very important that the products obtained are almost crystalline in nature, particularly this one. Particularly this one, when you look at the reactions given at the below portion of the table, it's particularly highlighted. You can see 2,4-DNP derivatives. They are yellow, orange or red solids useful for the characterization of aldehydes and ketones. 2,4-DNP, as is known as Borchers reagent or Brady's reagent, that in fact is the importance of that reagent and the reaction. The obtained products are yellow, orange or red solids with a characteristic sharp melting point. And it can be used as a characterization for aldehydes and ketones. That is the importance. Okay. And now the last one. There are 7 reactions. Now the last one with the semicarbazide. 7th one, semicarbazide. Carbonyl compound interacting with the semicarbazide. This is called a semicarbazide. Semicarbazide. And what is the product obtained? H2O out as usual. You get a semicarbazone. 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 So 7 important examples, including the involving the ammonia and the derivatives added to carbonyl compounds. Reaction number 1 with ammonia, you get imine. Okay. Reaction number 2, it is amine. You get substituted imine called Schiff's base. Reaction number 3, Z place OH group, hydroxylamine, product is oxime. Reaction number next, fourth one, right? Fourth one. Z place we have NH2, that is hydrazine, product is hydrazone. Phenylhydrazine, product is phenylhydrazone. 2,4-dinitrophenylhydrazine, product is 2,4-dinitrophenylhydrazone, and importance of that particular example we have discussed. And finally, semicarbazone. Hope you understand. Semicarbazide has to be specifically noted because you may fall in a trap. What trap, sir? What trap involved in semicarbazide? Can you identify a possible trap when you are dealing with the reaction of semicarbazide with the carbonyl compound? Don't you? Yes. There can be a trap. What it is? They may try to identify, they may try to trace students who are marking which NH2 is interacting. Is it this NH2 interacting or is it this NH2 interacting? Or can it be both? Which NH2 can interact in the reaction? Is it this NH2 or this NH2 or either of this? Or one getting priority over the other? Or only one? It's only one. It's only one, and it is this NH2 group. This NH2 group can interact in the reaction because the other one is this is amide, this is amine, this is ammonia and derivative. That's the basic group. This is amphoteric in nature. Amide it is. So which terminal of that NH2, which terminus NH2 is interacting in the reaction? It is this NH2, not this. Don't take this. This is to be considered. Because at the terminus of both, the molecule semicarbazide, there are two NH2. Here NH2, here NH2. So which NH2 involves in the reaction? That NH2. Because amide NH2 it's amphoteric in nature. In fact, many of you know the reaction is conducted in an optimum pH range, somewhat in the range of 4, 5, 5.5, in that range. That is a range of pH, very, very comfortable for this reaction. If the pH is 1, the reaction is not comfortable. If the pH is 10, the reaction is not comfortable. That also many of you may be aware of. Those who are not, please try to identify why. Why a particular optimum pH is always helpful in this particular reaction. A pH of 4.5, 5.5 is comfortable range in this reaction. If you have a pH 1, not necessarily you get the reaction happening comfortably. If you have a high pH, not necessarily the reaction is happening comfortably. Why? Many of you know. I'm just reminding you, that's all. Those who don't know, please try to understand why. Yes, that's about the reaction of ammonia and derivatives. Next one, already discussed the reaction. It is reduction procedure, reduction to alcohols. Aldehydes and ketones can be reduced to, aldehydes will be reduced to primary alcohol and ketones will be reduced to secondary alcohol by using either sodium borohydride or lithium aluminum hydride or catalytic hydrogenation. It can be done by lithium aluminum hydride or it can be done by little bit milder, even though sodium borohydride. It can be done by catalytic hydrogenation. Aldehydes will turn primary alcohol. Aldehydes are CHO. Here H2 is added. Here H2 is added and the result will be RCHHOH. You get primary alcohol. So aldehydes will give you primary alcohol. Ketones will give you secondary alcohol. Already we have learnt. While there is a special type of reduction called reduction to hydrocarbon part. Carbonyl group is reduced to hydrocarbon part Almost all of you may be remembering that very popular reaction, the so-called Clemmensen reduction and Wolff-Kishner reduction. Carbonyl compound treated with zinc amalgam and HCl. Carbonyl compound treated with zinc amalgam and HCl. The result will be O is out and is replaced by hydrogen. You get corresponding alkane part. The CO group converted to CH2 group. Clemmensen reduction. Clemmensen reduction. Meanwhile, we have a similar reaction where the carbonyl compound is first treated with hydrazine NH2, followed by treating with ethylene glycol, and KOH and heating. You get the same result. And that reaction probably you remember Wolff-Kishner reduction. Wolff-Kishner reduction. The purpose of both the reactions are basically same. The CO group converted to CH2 group. Say for example, if you take acetophenone. Suppose you are taking acetophenone. This is acetophenone. When treated for either Wolff-Kishner reduction or Clemmensen reduction, the result will be this O is out and you get that turn CH2. The result is you get ethyl benzene. You get ethyl benzene. This is what the purpose of whether you deal with the Clemmensen reduction or Wolff-Kishner reduction. But it is conducted in a different way. Clemmensen reduction, zinc amalgam with HCl. If you take a molecule which is sensitive to acids, avoid this method because it is conducted in acid medium. If you are taking a molecule which is sensitive to alkali, avoid this. Sensitive to base, avoid that because it is conducted in basic medium. So acid basic sensitive groups if present and if it interfere, it is you can choose. You can choose between Clemmensen reduction and Wolff-Kishner reduction. If you want that, you can select it. If you want to this, you can select this because it's giving same result but in a different way and different mechanism. So here we are using first added with hydrazine, then followed by heating with ethylene glycol and KOH, you get the same result. This is called a Wolff-Kishner reduction and this is called a Clemmensen reduction, right? So that is about two important reduction reactions, and our next discussion is oxidation. Next discussion is oxidation. See, aldehydes and ketones can be oxidized to carboxylic acids. As already learned in the previous chapter, aldehydes can be easily oxidized to carboxylic acid and there is no change in the number of carbon atom. So if we take a primary alcohol, which we were learning in the previous chapter, and even in this chapter also, primary alcohol easily oxidized to aldehyde, from there to carboxylic acids, while a secondary alcohol cannot be easily oxidized. Even if you oxidize, you are getting a ketone, and ketone cannot be oxidized under normal condition. We have to apply elevated condition. And you get a carboxylic acid with a lesser number of carbon atom. So that is the procedure. So if you take an aldehyde, say RCHO, upon oxidation with any good oxidizing agent or even mild oxidizing agent, you will get carboxylic acid, right? While if you take a ketone, RCO, suppose if you take RCH2CO R dash, just one general molecule taken, if it is taken for oxidation, number one, you have to apply elevated condition. You have to apply elevated condition, right? Now, if you try to oxidize, what will happen is you can get multiple different products. You may get multiple different products. Let me write the format like this: RCH2CO CH2 R dash. Suppose this is oxidized. See children, all of you know, I am just reminding you, it can be a oxidative cleavage over here. Let it be a cleavage over here, number one. The possible products are RCH2 will turn RCOOH. This carbon will turn carboxylic acid, and you get this as a carboxylic acid, and you get R dash CH2COOH. So you may get two different products, right? Two different carboxylic acids as a cleavage occurring at position 1. What about if the cleavage occurring at position 2? Suppose it is cleaved over here, say second cleavage if we take, what you can get is, you may get this as a carboxylic acid, that is the second case. You may get RCH2COOH, and this you may get as a carboxylic acid, R dash COOH. You see, you get 4 different products. Okay. For example, if you are taking CH3, if you are taking CH3, CH2, CO, CH2, CH, CH3, CH3. Just imagine this is what you take as a ketone, which is an unsymmetric ketone. What is the possibilities? What all possibilities are possible? You take the cleavage over here, you get a ethanoic acid, and this as a carboxylic acid. So you will get product number 1, CH3COOH, ethanoic acid, and what do you get? CH3, CH, CH3, CH2, COOH. That is another possibility, right? Now there is another chance of cleavage, as already we have discussed. It may be cleaved over here, right? Then the result can be propanoic acid. You get a propanoic acid, CH3, CH2, COOH, and CH3, CH, CH3, COOH, isobutanoic acid, like this. This is what happening. And you know which cleavage will dominate. Suppose if you are given with a ketone like this, CH3, CO, CH2, CH3. As discussed, it may be a cleavage over here, or it may be a cleavage over here. It may be 1 or 2, right? So which will dominate? Or is it happening almost 50-50 like that? What is the dominant type of cleavage that may happen if you take unsymmetric ketone for oxidation under elevated condition? A general observation what we have found is the keto group, the cleavage occur in such a way that the keto group retained with a simple alkyl group. That means whether this keto group is remaining with this group or that group, this is a simple alkyl group, so this cleavage will predominate, and you get acetic acid and acetic acid. You get 2 moles of acetic acid. And that is generalized as a rule. Many of you might have heard about it. It's so called Popov's rule. Popov's rule. What is Popov's rule? If you take a unsymmetric ketone for oxidation under elevated condition, the carbon-carbon cleavage occur and you get carboxylic acid, which predominantly may happen in such a way that the keto group is retained with a simple alkyl group. That is what happening and is called Popov's rule. Is it clear? Yes. So point number 1 regarding oxidation of aldehydes and ketones. Point number 1, aldehydes can be easily oxidized. Even with the mild oxidizing agent, aldehydes can be oxidized. Many of you know tolerance test is given by aldehydes, not by ketones. So mild oxidizing agents also can oxidize aldehydes but not ketones. And in ketones, if you go for oxidation, you get carboxylic acid with a lower number of carbon atom. If you take aldehydes, carboxylic acid obtained with the same number of carbon atom. That is the nature of the oxidation reaction. Okay? Yes. And here we go with the tolerance test. Here we go with the tolerance test. This is tolerance test for aldehydes. Any aldehyde, whether aromatic or aliphatic, any aldehyde, whether you take aromatic or aliphatic, when treated with the ammoniacal silver nitrate solution called tolerance reagent. Tolerance reagent, ammoniacal silver nitrate solution, when treated with any aldehyde or whether it is aliphatic or aromatic, what can happen is the aldehyde will be oxidized to carboxylic acid and metallic silver is reduced. Metallic silver is reduced and walls of the test tube turn silver mirror appearance and is called a very popular silver mirror test. Silver mirror test is answered by aldehydes. Silver mirror test is answered by aldehydes. Usually ketones will not. Ketones will not answer silver mirror test because the silver mirror test conducted by tolerance reagent. What is tolerance reagent? Ammoniacal silver nitrate solution. It is a mild oxidizing agent. Being a mild oxidizing agent, it can oxidize only aldehydes but not ketones. Is it 100% all ketones does not give silver mirror test? Not like that. There are special cases of ketones which can give silver mirror test. I am leaving for your investigation purpose. I am leaving that matter for you to investigate what kind of ketones may give silver mirror test. Usually all aldehydes, whether aromatic or aliphatic, will give you silver mirror test, while ketones cannot. But certain type of ketones can, that I am leaving to you. For your investigative study, I am leaving that matter. Of course, that is competitively important. Okay. Anyway, coming to the conclusion over tolerance test. Tolerance test is answered by aldehydes, whether aliphatic or aromatic, while ketones will not give tolerance test. We have Felling's test. Another one is Felling's test using Felling's solution. Using Felling's solution, we conduct Felling's test. What is Felling's solution? It is Felling's solution A and Felling's solution B. Felling's solution A is nothing but aqueous copper sulfate solution. And Felling's solution B is Rochelle salt solution. That is sodium, potassium, tartarate. Sodium, potassium, tartarate called Rochelle salt. What is tartarate? Tartaric acid. This is tartaric acid. This is the acid present in tamarind called tartaric acid. It's a dibasic acid formed by a salt. There can be a two salt it may form, and you see that sodium, potassium, tartarate, that is popular called Rochelle salt. So that is referred as Felling's solution B, while Felling's solution A is called copper sulfate solution. So copper sulfate solution with the sodium, potassium, tartarate, that together it is called Felling's reagent, or Felling's that corresponding test is called Felling's test. What is Felling's test? You take aldehyde. Aldehydes will respond to Felling's test. Aldehydes are oxidized to carboxylic acid, while Cu2 plus reduced to cuprous oxide, you get reddish brown precipitate. Reddish brown copper oxide precipitate is obtained, and that is called a Felling's test. Remember, Felling's test is answered not by all aldehydes, but only aliphatic aldehydes. Only aliphatic aldehydes. While aromatic aldehyde does not respond to Felling's test. Tollens test is answered by both aliphatic and aromatic, while Felling's test is answered by only aliphatic aldehydes. It is slightly milder than the other one. And there is a similar test like Felling's test called Benedict test. Benedict test. Quite similar. Benedict test. Benedict test. What is Benedict test? That is also nothing but copper sulfate with sodium or potassium citrate. Sodium, potassium citrate, a salt of citric acid. A salt of citric acid. Here we were taking tartaric acid. There we take citric acid. Sodium or potassium salt of citric acid with the copper sulfate solution called Benedict reagent. And the purpose is same like Felling's solution. And what is citric acid? Citric acid. This is citric acid. COOH, CH2, CCOOH, OH, CH2, COOH. This is citric acid. 1, 2, 3. 2-hydroxypropane. 2-hydroxypropane. 1, 2, 3. Tricarboxylic acid. What is tartaric acid? 1, 2, 3, 4. 2,3-dihydroxybutane dioic acid. 2,3-dihydroxybutane. 2,3-dioic acid. Sorry, 2,3-dihydroxybutane, simply dioic acid, because it is terminal only. While here it is, there are 3 COOH. So this is taken as the principal principal chain. It is 1, 2, 3. 2-hydroxypropane, 1, 2, 3 tricarboxylic acid, citric acid, and sodium potassium salt of citric acid with the copper sulfate taken as Benedict solution, and the purpose served is same. Okay. So that is regarding oxidation of aldehydes and ketones. Aldehydes are easily oxidized to carboxylic acid, while ketones are not so. And if you take unsymmetric ketones, the cleavage dominantly occur in such a way that keto group is retained with a simple alkyl group, Popov's rule. And then followed by Tollens test, silver mirror test, and then Benedict test, Felling's test. Benedict test is not in the textbook. Felling's solution, Felling's test is available in the textbook. That's about oxidation reactions. And now we have some special oxidation of methyl ketone, haloform reaction. Haloform reaction, very, very popular reaction in organic chemistry. Haloform reaction. Haloform reaction. See, haloform reaction is given by those organic compounds, aldehydes or ketones or even alcohols, those organic compounds which contain a methyl keto group or methyl carbinol group. So those organic molecules which contain methyl keto group, this is called a methyl keto group. Methyl carbinol group. Methyl carbinol group. This group is called a methyl carbinol group. So those molecules which contain methyl keto group or methyl carbinol group. See, in fact, we need this, but this can be converted to this. Therefore, this is also possible. Okay. Other than carboxylic acids and derivatives, it is not possible to conduct such a reaction in acids or acid chlorides or anhydrides, even if it contains such a group. So those molecules which contain methyl keto group, methyl carbinol group, other than acids and derivatives, may undergo a reaction called a haloform reaction. May undergo a reaction called a haloform reaction. See, if you take acetone, there contain methyl keto group. So this can give you haloform test. If you take isopropyl alcohol, CH3, CHOH, CH3, this contain methyl carbinol group. This contain methyl keto group and this contain methyl carbinol group. This will give you haloform reaction, right? But remember, if you are dealing with, say, acetic anhydride, which is acid anhydride, this is acid anhydride. Remember, there is a methyl keto group, but the reaction is not applicable because ultimately haloform reaction is a oxidation reaction, and acids and derivatives are final oxidized product. That's why. So other than carboxylic acid and derivatives, not acids, not acid chlorides, not acid anhydrides like that, any other molecule, maybe aldehyde, ketone, alcohol, which contain either methyl keto group or methyl carbinol group, when treated with when treated with halogen and alkali, you will get a haloform. When treated with the halogen and alkali, you will get a haloform. Let us see the reaction. Say with the acetone. Say with the acetone, CH3, CO, CH3. There is a methyl keto group. This is treated with the chloroform and alkali. Or it can be any halogen, X2 with alkali. It may be I2 with NaOH, or it may be simply written as NaOI. So it is written like this, like this, like this, or like this, doesn't matter. All our principal character is same. So when such a molecule treated with the halogen and alkali, you see what actually happening is this carbon is getting chlorinated and you get CH3, CO, CCl3, chlorinated ketone, trichloroacetone. And now this is hydrolyzed. This upon hydrolysis, it is going to break here, and this part of the molecule is giving as an oxidative product. You get CH3, COONA, as it is an alkaline solution. You get a salt, and that is oxidation reaction. And here we have the particular observation. This carbon, in fact, this carbon which converted to CCl3 is converted to CHCl3, the hero of the show, chloroform. And that is what the reaction. That is what the reaction. So any such molecule when treated with a halogen or alkali or sodium hypohalite, all are same. You will get a series of reaction where finally you get a chloroform, haloform, and the other part of the molecule will turn carboxylic acid. Let me explain one more example. Suppose we are dealing with this kind of molecule. See that? Suppose we are dealing with this kind of molecule. See? This is capable of giving such a reaction because there is methyl carbinol group. This is methyl carbinol group. Imagine this is treated with chlorine and alkali, or any halogen and alkali. This is treated with chlorine and alkali, say NaOH. What the reaction will happen is this carbon will be converted to CHCl3, chloroform. and the remaining part of the molecule, this much part of the molecule will be converted to carboxylic acid. And what you get is that remaining part, there is carbon and that will be converted to carboxylic acid salt like this. This is ultimately an oxidation reaction. And acids and derivatives are oxidized product. That's why they are unable to proceed further in such a case. Hope it is clear. You see how the commercial chloroform is produced. Commercial chloroform produced from ethanol. Commercial chloroform produced from ethanol. You see, this is ethanol. And there is methyl carbonyl group, CH3, CH2OH, CH3, CHOH, methyl carbonyl. Imagine this is treated with bleaching powder. I am talking commercial operation, bleaching powder. Bleaching powder acts as a good oxidizing agent. Bleaching powder acts as a good oxidizing agent, and step one process is oxidation. Ethanol oxidized to ethanol. Ethanol oxidized to ethanol. And don't you see CH3CO? There is methyl keto group. And that bleaching powder is able to give chlorination reaction. Second step, chlorination reaction. Second step, chlorination reaction. This carbon will be chlorinated. You get a CCl3CHO called chloral, trichloroethanol, chloral. And final will be hydrolysis. Is going to cleave over here. You get a commercial chloroform CHCl3 plus HCOO minus. So that is haloform reaction. For this reaction to function and operate, you should have in the molecule a methyl keto group, CH3 C double bond O group, or methyl carbonyl group, CH3 CHOH group, which must be other than acids and their derivatives. Okay. Say acid is represented here in the textbook. Suppose we take this example. This particular given example. Don't you see it contain methyl keto group? This molecule contain methyl keto group. This is methyl keto group. When treated with NaOCl, what is NaOCl? Chlorine with NaOH is called NaOCl. And what is the reaction happening? As I said, the carbon of methyl keto, this group is converted to chloroform. And the remaining part of the system, what is the remaining part? This is the remaining part. That will be converted to oxidation product. It is converted to oxidation product. So the carbon of that methyl keto group converted to haloform, and the remaining part of the molecule converted to keto. I mean carboxylic acid salt. Okay. That is one of the very famous reaction from I won't say this particular chapter. This reaction is applicable in entire organic chemistry. This reaction is very popular. Haloform reaction. Okay. Yes. Next, it is special reaction of aldehydes and ketones, which are derived by the acidic nature of alpha hydrogen atom in aldehydes and ketones. Very, very popular reaction. All of you remember aldol condensation. The reaction is triggered by the acidic nature of alpha hydrogen atom present in aldehydes and ketones. Understand? Alpha hydrogen of aldehydes and ketones having acidic character. And that in fact is triggering the very popular reaction aldol condensation. First of all, let us see the acidic nature of alpha hydrogen. Acidic nature of alpha hydrogen in aldehydes and ketones. if you take an aldehyde, say ethanol, this is an aldehyde, say ethanol, ethanol. This is the functional group, this is alpha carbon, this is alpha hydrogen. There are 3 alpha hydrogen. That alpha hydrogen carry some acidic character. How it is able to have some acidic character? Very simple logic. You see, it may be attacked by a base comfortably. It may be attacked by a base comfortably. OH minus with H plus will turn water, and this electron pair will be shifting to carbon, and you get CH2 minus, a carbanion. CH2 minus, a carbanion. You get a carbanion. And that carbanion is stabilized by the nearby electron withdrawing group. This carbanion may be stabilized like this. Look at the resonance. And due to this resonance stabilization, the carbanion is stable. Since the carbanion is stabilized, that hydrogen may be released as H plus. Hope you understand. How we say alpha hydrogen is acidic. It may be released as H plus. It may be interacting with the base, released as H plus. Why it is been able to release it as H plus? Not strongly acidic, but still. How it is able to be released as H plus? Because of stability. The obtained carbanion stabilized by resonance, stabilized by the nearby keto group, right? If you take acetone, same scenario. If you take acetone, this is acetone. This is acetone. A base can be, this is functional group, and this is alpha carbon, and this is alpha hydrogen, where the base can be easily attacking that alpha hydrogen, and this electron pair will be shifted to carbon, and you get CH2 minus CO CH3. The electron withdrawing effect of this nearby group, electron withdrawing effect of this group is able to stabilize the carbanion by resonance like this. So due to such a resonance stabilization, carbanion is stabilized, due to which H plus is released. Is that clear? This acidic nature of alpha hydrogen is triggering aldol condensation. Aldol condensation is in fact a condensation reaction given by aldehydes and ketones with the alpha hydrogen atom. Aldehydes and ketones with the alpha hydrogen produces aldol condensation. It's a simple condensation reaction. It's a simple condensation reaction which is triggered by alpha hydrogen atom. So this is what that happening. Functional group, alpha carbon, alpha hydrogen attacked by a base, you get a carbanion stabilized by resonance. This acidic nature of alpha hydrogen is demonstrated in the very popular reaction aldol condensation. And that is what the point of discussion next, aldol condensation.